This is a video on the heat of neutralization lab. You could see the information on in the lab manual. That's on page 117. That's where the lab starts. Basically, the lab involves taking some hydrochloric acid, somewhere around 100 milliliters of hydrochloric acid, and it's a 2 molar hydrochloric acid solution, combining it with about a 2 molar sodium hydroxide solution. We're only using about 50 milliliters of that. It's an acid-base neutralization reaction, and that acid-base neutralization reaction is going to produce heat, similar to the last lab reaction number 12 with the net ionic reaction lab, where you produced a little bit of heat. You also get some salt water with that reaction. Kind of wrote out the net ionic equation for this reaction. Again, hydrochloric acid dissolved up in water, aqueous solution of sodium hydroxide. You end up with sodium chloride, aqueous, and water as a liquid stage. I broke things down ionically. Spectator ions, your net ionic reaction is basically the hydrogen ion combining with the hydroxide ion to give you water. Now, there's only bond formation that forms in this acid-base neutralization reaction. Because of that, it is going to be exothermic. Heat is going to be produced with this reaction because you only have bond formation that takes place. Now, you can't measure heat directly. What you can measure is a change in temperature. So this delta T, or this little triangle T, that represents a change in temperature. So basically in the lab, you need an initial temperature of a solution and you need the final temperature of a solution. You subtract those two and you're going to get a change in temperature. So heat can't be measured directly, but we can measure it indirectly by looking at a change in temperature. There's also some other things that factor into calculating this Q value, or this heat value. You need to know how much of the substance you have, or the mass of the substance. In this particular lab, you have a liquid solution. So with a liquid, we definitely know the volume. If you also know the density, you take volume in milliliters times density, which is usually grams per milliliter, and you're going to get a mass in grams. This value of S stands for the specific heat, and the specific heat of the solution that we're using is around 3.89 joules per gram degree Celsius. So in order to calculate the heat that's produced, you just take the mass of solution, multiply it by the specific heat, multiplying it by the temperature change of the solutions. Heat of neutralization, or the enthalpy of the reaction, is calculating by taking the heat of the reaction and dividing it by the moles of the limiting reagent. So Q divided by the moles of the limiting reagent is going to give you the enthalpy, or the heat of neutralization for this reaction. Your data chart, the Excel sheet, looks similar to this. I have some information filled out up here, the volume of sodium hydroxide that's used to make a watered-down solution of sodium hydroxide. To standardize it is 10. Your molarity of hydrochloric acid was 2.000 molar. Your density of the solution, there's that density value, 1.04 grams per milliliter. This information I actually got from slide number 4 of the dry lab. So the first part of the lab involves standardizing a sodium hydroxide solution. We standardize that, again, because sodium hydroxide is hygroscopic. We're going to use a primary standard, which is KHP. And in the slide it shows, 0.821 grams of KHP were measured. An initial burette reading, I read it as 0.30. A final burette reading, 18.65. Subtracting those two, I get 18.35 milliliters is what it took to get to that light pink endpoint when I had 0.821 grams of KHP. You can see I've calculated moles, moles, and molarity. Let me go into detail with that. Again, all I did was put together an example of the data that I've already collected. There's your 0.821 grams. There's your 18.35 milliliters of sodium hydroxide. Using a factor label approach, I start out with the 0.821 grams of KHP. I know the molar mass of KHP. That'll give me grams per moles. Now I know the number of moles of KHP. Notice in this chemical reaction, it's a 1-to-1 KHP to sodium hydroxide mole ratio. So there's your 1-to-1. Gives me this many moles of sodium hydroxide. Again, that's how many moles of KHP you have. That's how many moles of sodium hydroxide you have. To calculate the molarity of the sodium hydroxide, since that's what you're trying to figure out, you take the moles, divide it by the liters. Now again, we have 18.35 milliliters, 0.01835 liters gives me this particular molarity. So for trial number 1, there's my molarity. Slide 5 has trial number 2. Slide 6 has trial number 3. So you're going to end up with 3 molarities. You're going to calculate your average molarity, and whatever this molarity is, you're going to multiply it by 10, and that's going to be your concentrated sodium hydroxide. Again, that's where this number 10 came into play. You actually diluted things to standardize the sodium hydroxide. You just take this value, multiply it by 10. That's going to be your molarity of the concentrated sodium hydroxide. All right, now we're down to determining the heat and neutralization. Again, I got this information from slide number 4. Volume of sodium hydroxide used, volume of hydrochloric acid that was used. And again, you could see much, much less sodium hydroxide is used than hydrochloric acid. That ends up being the limiting reagent. From slide number 8, I have 3 temperature readings. That's the initial temperature reading. Here's my average. From slide number 9, I have 3 final temperatures. Again, here's my average final temperature. So I'm going to take this information and I'm going to transfer some of it down here. Well, the number of moles of sodium hydroxide used in the reaction, you basically need to know your molarity. And again, my molarity is going to be not 0.219, but it's going to be 2.19 in this particular case. Again, yours is going to be different because you're going to have a different average value. But I'm going to use the concentrated sodium hydroxide molarity, which again, 2.19, multiply it by this volume in liters. Remember, molarity, moles per liter times liters, will give us the number of moles. Hydrochloric acid, I have 2 molar hydrochloric acid, multiplying it by the volume in liters will give me the moles of HCl. And that should not change because this value don't change for trial number 1. So this is the moles of sodium hydroxide used in the reaction. That's the moles of hydrochloric acid. Again, if I look at the moles used, this number, the moles of sodium hydroxide, is much less. That is the limiting reagent. Delta T, change in temperature. All I'm doing is looking at your final temperature, initial temperature, subtracting those 2 values, and I'm getting 8.8 degrees Celsius. Total volume is sodium hydroxide plus hydrochloric acid. Those 2 values added together will give me this value. Notice this value, the mass of the solution, is not the same as the volume. That's because we have to factor in the density, right? This is milliliters, this grams. The density of this solution is 1.04 grams per milliliter. So this number times 1.05 will give me the mass of the solution. So now we can calculate Q in joules, Q in kilojoules, and your delta H, or your heat of neutralization, in kilojoules per mole. Again, I'm using the values from the dry lab to go through this example. To determine Q, again, you look at the mass times the specific heat and the change in temperature. So we already determined change in temperature was 8.8. Our constant for the value S is 3.86. Again, that's the specific heat of the solutions. And our mass, we determined it at 157.6. So we just take all those values, multiply it together, and I get around 5,353 joules. I'm looking here at the 8.8 degrees Celsius. That's two significant figures. So all I need to do is report two significant figures. 5.4 times 10 to the third joules. There's 1,000 joules in a kilojoule, so that would be 5.4 kilojoules. Should that sign of Q be positive or negative? Well, it's an exothermic reaction by definition. If it's an exothermic reaction, this value for Q should be negative. A negative heat value tells you it's an exothermic reaction. Heat is given off to the surroundings, and again, we're measuring the change of temperature of the surroundings. So that means through the reaction to the product, they're actually losing heat energy. So therefore, it's negative. So it should be negative, that value for Q. So now we have this value and we have this value. One step further is this delta H. And again, I'm going to draw your attention back to number of moles of sodium hydroxide, 0.115, because you'll see that on this next calculation. The heat change per mole of the limiting reagent, we know the limiting reagent is sodium hydroxide. How many moles of sodium hydroxide we have? Well, we take the molarity. Again, you can see I use 2.19. Yours will be a little bit different because you're going to calculate the average molarity. This 0.0525, that was the volume of the sodium hydroxide I used. Again, got that off the slide with the graduate cylinder. So I know we had 0.115 moles of sodium hydroxide. To calculate the enthalpy, or the heat of neutralization, we're just taking the Q value, that minus 5.4 kilojoules, dividing it by the number of moles we had of the limiting reagent, 0.115. And we get the heat of neutralization of minus 47 kilojoules per mole. And again, that sign of delta H is negative due to it being an exothermic reaction. So I went through basically trial one here, trial one here. You will need to follow those steps to be able to do trial two and calculate your average heat of neutralization. Similar to up here, I went through one example for trial one. You'll need to do trial two and trial three.